So what is Femap? Femap is a CAD and solver-neutral advanced engineering environment analysis dedicated to finite element analysis, and it's developed by Siemens PLM software. Femap has in-depth detailed functionality required to accurately model real-world parts and assemblies. And Femap can be used to model systems across various industries and perform engineering analyses for structural, heat conductivity, and fluid flow problems. So introduction to our demonstration. This will be a live demonstration, continuing the model creation that was started in SDA's Manipulating Geometry and Meshing in Femap webinar that was done in November of 2014. We will give an introduction to the capabilities of Femap for creating finite element models. We'll first start by reviewing the meshing that was completed in the first webinar using the meshing toolbox. And then we will complete the FEM with some rigid and mass elements. And then we'll set up some static loads and constraints and finish by setting up and running normal modes and static analyses. So we're going to switch over to Femap now so we can start the demonstration. So this is a look at the bracket that we meshed in the first webinar. So we took this bracket and we isolated the solids that we wanted to plate mesh, and we created some surfaces from that. So if we open up the layer that we put our surfaces in, you can see the mid-surfaces that we created in the first webinar. Now we're going to go back and mesh these surfaces using the properties that were created based off of the material that we created in the first webinar. So to do this, we're going to go over to our meshing toolbox, go over to mesh surface, and we're going to select our first property. We're going to set our mesh size, and we're going to select map mesh, and then we're going to go into dialog select and select the surfaces that we want to mesh first. So we're going to select all of these surfaces that have the same thickness that we created a single property for. And we could select multiple surfaces at once as well. And we're going to check to see if it's selected the right surfaces. We have everything there. Okay. And now we have meshed those surfaces. Now we're going to select the next property and select the surfaces for that property. It's going to mesh those. And then we're going to go in and mesh the last surface with the last property. So now we have the mesh for our bracket, and we're going to go in and we're going to check the free edges to make sure that we don't have any unnecessary free edges. As you can see, there aren't any, so we're good with that. So the next step that we're going to do is we're going to start adding some rigid elements so we could add some constraints and some point forces. So to do that, we're going to go into model, element. We're going to change the type over to rigid. And these are going to be completely rigid RBE2 elements. And we're going to select our nodes that are on these pads here. So we're going to use our circle select and just pick all the nodes. And then we want a new node at the center because we don't have currently one where we want to put a node. So that'll automatically create a node at the center of the circle. And we're going to repeat for the other pads. So we have all those nodes there. And now we're going to go to the other ones. All right, that one's done, and now the last one. All right, so all those elements are created. Now we're going to create one more RBE2 element for the point force that we're going to apply to this. And that's going to be on the back of this bracket here. And create a new node at the center. All right. So now the next step is if we look at the solid geometry from this bracket, we can see that there's a big component in the middle here that we want to model with a mass element. So to do that, we're going to go into our tools, mass properties, and solid properties, and we could select a solid. And Femap will measure the volume of that solid, and it'll automatically create a mass element and a node for that mass element given a density that we provide for it. So we'll just provide an arbitrary density. We don't want to link it to the mesh yet. So now if we turn off the solid, we can see that it created a ConM2 mass element. And if we look at the property of it, we can see that it applied the moments of inertia that it calculated automatically based off of the geometry. And it applied that mass that it measured for it. So now we're going to hook this up with an RBE3 element, which is usually used to connect mass elements to structure. And to do that, we're going to go to Model, Element, and we're going to flip over to an RBE3 element. Now our dependent node is going to be the mass element node, and our independent nodes are going to be nodes on the bracket here. So to pick our nodes, we're going to flip back on our geometry so we could see where this component is attached to, and we could turn off the surfaces so we can easily see the mesh underneath it. And then we're going to go through and select the nodes that we want to attach the bracket to. We'll pick all the nodes near the little connection pieces here. These. All right, now that that's done, click OK. And now we have an RBE3 element that connects our mass up to our bracket. We'll flip off our geometry again, and now we have our completed mesh. So the next thing that we're going to do is we're going to set up our loads and our constraints. Now to do that, we can go to the Model Info pane, right-click on our constraints, and select New. We'll just label it as Fixed. So that'll create a constraint set. And to do that, and to create the actual constraints, we're going to right-click on their constraint definition, select Nodal, and we're going to select the nodes of the RBE2 elements that we created on the pads. Click OK. And this is where you're going to show your constraints degrees of freedom that you're going to apply to those nodes. And those are going to be based off a coordinate system that you define. So the coordinate system we're going to pick is the basic rectangular coordinate system, and we're going to select Fixed. And we're select OK. And now we have constraints that are applied to those nodes and those RBE2 elements, which spread it out to the bracket itself. The next thing we're going to do is we're going to create our loads. So we're going to select New, and the first one we'll create is accelerations. So we'll open up that load. And so accelerations we're going to apply as a body load. And to do that, we're going to go to Edit. And these are applied based off a coordinate system that you define. And we're going to apply some translational accelerations. And we'll apply about 10 Gs in all three directions. We do that by setting our AX, AY, and AZ. And as you can see in our body loads, you could apply multiple sets of loads, including thermal, some rotational velocities, rotational acceleration, things like that. Click OK. Now we created our acceleration loads. Next thing we want to do is we want to create our point load that's going to be applied to the RBE at the back of the bracket. So we're going to go to New, Point Load, open that up, select Nodal, we'll select the node on that RBE2 element, click OK. And these forces, the X, Y, and the Z, are applied based off the coordinate system that's defined there. We'll apply 10 pounds in the X. Click OK. So now you can see that we're showing our constraints and our forces, so you can see the vector of the point force that we're applying here. In addition, you could also see the constraints that are being applied at the nodes. If we toggle is on, they'll disappear. So now that we have our constraints and our forces, we're ready to create our analysis sets. First thing we're going to do is we're going to create our modal run. So analysis program is going to be NX Nastran, and our analysis type is normal modes. Now for most of these sections, we're just going to go with the defaults that Femap provides. Flip through here. So this is the first section that we care about as our modal analysis. This is where we're going to set if you have a range of interest of modes you want to look for, or if you want to define the number of modes you're asking for. This is where you would set those options. We're going to leave the default as 10 for right now. And then now into our master requests and conditions is where we're going to set our boundary conditions. And we don't want to apply a constraint yet. The first thing we're going to do is we're going to run a free modal analysis. And that's going to be a good check for our model to make sure that we have our 6 rigid body modes that are near 0, and then no other modes that are really low near 0. And our output requests, this is where you're going to define what you want to get from your analysis. And you can get displacements, constraints, applied loads, strain energy. We're going to leave those as they are right now. Click OK. And now we can click the Analyze button. So this is going to open up your analysis monitor, and we can minimize that. That'll just give you some information as the analysis mode is running. As you can see, it already completed, and it outputted our results right into the file. So if we open this up, we could see that we have 6 modes that are near 0, and our 7th mode is much higher than that. So that's a good model check to show that we have a good model here. Now, if we want to go and animate or show what these modes look like, we can go and do that, and we could select our deformed view, or you can also do an animated view to see what the mode actually looks like. So you can see if we flip through these, and the last one. Okay. So now that we did that, we don't need these results anymore, so we can delete them. So now we're going to go back into our mode set, and we're going to apply the constraints that we created. So to do that, we could just go right into our master requests, and we can go right into our boundary conditions. We'll edit and apply our constraint, and we'll rerun it. That should just take a second here. Now we have our results. So we could show our deformed view again. We could see that's what our first mode looks like. We can also show a contour view. So right now this is outputting our strain energy. So this is a contour plot of the strain energy for this mode. Now we could play with what the contour is showing by going into our post-processing toolbox. So here we can show the deformed view. We can open up the deformed view tab first, and here we can play with what our output vector is and what our output set is. So right now we're just showing the first mode. We can go in, we can select the second mode if we want to, and then we could also change what the output vector would be. So right now we're showing strain energy. If we flip over, we could show what a contour plot of the total translation would be, or not a contour plot, but the deflection plot. We can also change what the scale would be. So if we wanted to up the scale or lower the scale, we could change that right here. And you could change that also over to actual deformations instead of a % of the model. Next, we're going to go into our contour section here. And here's where we can change what contour plots are being shown. So right now we're showing strain energy. If we wanted to, we could go and flip over to total translation, and we could see that the contour plot changes for that. And there's other options and things you could transform the data in here to show for outputting pictures and things of that sort. So now that we've shown our modal run results, we're going to go and we're going to set up our static analysis results. So go back to the analysis set manager. We're going to create a new one. Flip our analysis type over to static. We're going to set our constraint here first. And we're not going to set a load because we're going to set both loads up to run for 2 different cases. So it doesn't have to, we don't have to set up 2 different analysis sets for both loads. We can set up 2 cases within the one analysis run. Output requests will leave what we have here. So now we're going to set up our 2 different cases. So the first case will be the accelerations. And we'll set what load we want, and that will be the accelerations. And the constraints are being applied from the master, as opposed to, if you had separate constraints, you could apply them here as well. And then our outputs are also set from the master. And now we'll set up our second case. That'll be the point load. set the load for that. Okay. So now that we have our static analysis set up, we can actually go in and preview what Femap is writing to Nastran. So here you can see the bulk data deck that Femap is outputting straight to Nastran. And you can see the case control here, so we can see that you have the two subcases set up and their loads for each subcase, in addition to the constraint that's being applied for both subcases written up here. You can see all the coordinate systems, the loads, the constraints, and your whole model being written here. And if you wanted to, you could actually even go in and edit the bulk data deck manually. Now from here we can run our analysis by clicking Analyze. And we have the output for our two static load cases. So the first one is our accelerations. We'll go back over to the post-processing toolbox. And as you can see, it's showing total translation, but now we have other options since we select different options for our outputs. So as you can see, Femap, you can output your von Mises stress, and Femap calculates all that. Turn off our nodes so we can see that a little bit better. And you can see the contour plot here of your von Mises stress that Femap is calculating. And you could also change over to the second output, the second case, if you wanted to. In addition, over here, we could set our levels. So the contour plot is based off the color bar over here. We could set exactly what the color bar levels we want to be. So you could change that from automatic over to max min, and we could set our maximum level on the contour and our minimum level. You could also change the color bar and all sorts of things that you want to do to create your contour plots. So now that that wraps up our demonstration for that. Flip back over to the presentation. So if you want to learn more about Femap, we have a book that was written by an employee at our company, Eric Gustafson. And it was developed for quick learning. And the idea for this book was born out of a need in our own office to train engineers and quickly bring them up to speed in Femap. This is a great addition for offices that work in structural analysis. We are also a Siemens PLM channel partner, and we provide first-line support for Femap with NX Nastran. And for our existing customers, those are our points of contact right there, our email and our phone number. Do we have any questions?
You had one question. What does strain energy mean in a modal analysis? Are the deflections arbitrary? Or to describe strain energy as best you can.
You have a good...
I answered it online. But
okay.
Basically, strain energy is a nice plot that'll tell you what part of the structure is deforming during the mode shape. So if you need to stiffen it, it can point you to where you need to stiffen. The displacements that are presented are scaled arbitrarily, right? So they're relative to each other. They make sense. But a deflection per se does not mean you have strain energy, right? If the channel that Alex is working on, if the centerpiece is bending and the sides are just kind of going for the ride, they won't have any strain energy, but will have a lot of displacement.
Any other questions? Thank you for attending the webinar. That will conclude our presentation for today.